Hello everybody. In this video, I'm going to walk you through a couple of examples for one-sided hypothesis tests, right? So remember, if you think back to some of the other videos, you can have a one-tailed or a two-tailed test, right? This video is going to focus on one-tailed tests. Okay, so let's go ahead and jump right into it, y'all. So this hypothesis test is for an experiment that we simulated in class. So the claim is that my younger brother, who really loves sports and thinks he's really good at basketball, claims to make 80% of his free throws. So we're going to perform a hypothesis test on his claim at the 5% significance level, right? And just as a reminder for you, he made in a sample of free throw shots, he made 32 out of his 50 shots. Right? So we're going to go through the 8 steps, go through every step of phantoms, right? So that you can see how a complete hypothesis test is done. Okay, so the first step is the parameter. So we have to state the parameter that our test is going to examine. So we are testing the claim that the true proportion of shots made, and that's P, is 0.8, right? Or you could say 80%, right? i.e. 80%. Okay, so that's our parameter. Okay, it's a good idea when you're doing the parameter part that you state both the actual variable, so P in this case, and what it actually stands for, which is the true proportion of shots made. Okay, step 2 is your hypotheses. So we have to state the null and the alternative hypotheses. Remember, the null is like the claim that's being made, it's the status quo, and the alternative is what we think will be true. Okay, so my null hypothesis is that P, the proportion of shots made, is 80%, so 0.8. And then my alternative hypothesis, if he only made 32 out of his 50 shots, my guess is that the true proportion is actually less than 80, right? I actually don't think he's as good as he claims to be, okay? All right, step C is the third step. A stands for assumptions. Okay, so it's the 3 assumptions that you've been checking all throughout this unit and in the last unit. Okay, so the first is this a random sample? And it's not technically stated in the problem, but it's reasonable to assume that the sample is a random sample of all shots he's ever taken. Right, and I should clarify that this is free throw shots, right? Right, so this is reasonable, basically. Okay. Second, is the population larger than 10 times the sample, right? So what I'm going to do is do 10 times the sample size, and he took 50 shots. That's 500, which is definitely less than the total number of shots he's ever taken, right? Definitely. Okay. And then lastly, you have to check your success fail / large count. So we're testing NP, which is 50 times 0.8, and that's 40. So we're good there. That's greater than or equal to 10. Okay, and then we have N times 1 minus P, which is 50 times 0.2, which that is exactly 10, which is still okay though, because we're testing to see if each of these is greater than or equal to 10. So we're good there. Okay, so those are our 3 assumptions. Next step, N, name the test. Okay, so first question you ask is how many, meaning how many samples are you dealing with? So this is just one sample. So this is a one sample test, right? And then are we talking about means or proportions? This is proportions. So this is a 1 proportion Okay, and then Z or T, this is a Z test, right? Remember that for proportions, Z is the type of test that we're dealing with. We're not going to get to T tests or T intervals until we deal with means, which is the next unit, okay? And they say, oh, also set an alpha value, right? So we were told in the problem to perform a test at the 5% significance level. So that is my significance level. So alpha is 0.05. Okay. Recall that if they don't give you an alpha value, they don't give you a significance level, 5% or 0.05 is a safe bet. Okay. All right. That's the first 4 steps. So you've done 4 out of the 8 steps, just setting up the problem. Okay. What you probably noticed when we did confidence intervals, and what I'm assuming you are probably noticing here, is that a lot of the stuff that you do in these hypothesis tests and the confidence intervals is not straight arithmetic, right? Like you do a lot of setup and defining things as well as interpreting things, right? And the math is kind of like that chunk in the middle, okay? So that's what we're going to get to next. T and O are the math steps, right? So this is where you actually do some arithmetic. So T stands for test statistic. So here we're going to calculate our Z value that we're going to use to find the probability, okay? So we have a couple of things that we need. One moment, please. Yeah, this is not going to give me the symbols that I want, unfortunately. So I'm going to have to write this out. Totally fine. Okay. So we need, in order to find a Z value, we need our data point, which is P hat. We need our true population proportion, which is P. And then we also need our standard deviation, which is the standard deviation of our, technically standard deviation of our sampling distribution, okay? And then after that, we can calculate Z. So P hat is 32 out of 50, which best thing to do is convert that to a decimal. So that's 0.64. Did not give myself enough space here. Okay, then P comes from our hypotheses, comes from our claim. So that's 0.8. So 0.8. Okay, then my standard deviation is the square root of P, so 0.8, times 1 minus P, so 1 minus 0.8, all divided by N, which is 50, right? So just as a reminder, your sample size here is 50, because he took 50 shots. Now, reminder, okay, because we have a possible value for the truth, right? We have a parameter value. You should always use that if you have it when calculating the standard deviation. So don't use P hat inside of your standard deviation calculation for hypothesis tests. The only time that you're going to do that is with confidence intervals, because with confidence intervals, you don't actually know the true value. Okay, so let's use this now to calculate our test statistic, which is our Z value. Okay, so remember, it's the statistic, so P hat, 0.64. Actually, you know what? I'm going to write this out with the actual equation here, just so that you all can see it for this first one. Okay, so the formula is P hat minus P divided by your standard deviation that you calculated. Okay. Now, on the actual AP test, this is another one of those things where people are like, okay, do they give me these formulas because I really don't want to have to memorize these? They do, in fact. They do give you all of these formulas, okay? Maybe not specifically this Z formula with the P hat and the P and the standard deviation, but they do give you, let me find it up here. They do give you, or not, possibly not. I'm trying to find what they do actually give you on the, No, I can't find it. What they give you on the, oh, it's this guy right here. They do give you this formula, right? So you just have to know what the statistic, the parameter, and the standard deviation are. But they do give you the formula for standard deviation of the statistic, which is nice. Sorry, little detour there. Okay, so I'm going to go ahead and plug my values in here. So p hat is 0.64 minus my proportion, my population proportion, my claim is 0.8 divided by whatever this standard deviation is. So really quickly, I'm going to plug this into my calculator to get what this is. So when I did, I got 0.0566. Okay, 3 to 4 decimal places is usually fine when you are working with your standard deviation, right? And then just plug that into your calculator. So when I plug this into my calculator, I got negative 2.827. So this is my test statistic. Okay. Right, that number right there is my test statistic. Okay. All right. Then next we have to obtain our p-value. Okay. So this comes from the normal distribution, right? And your either the Z table or norm CDF. So really quickly, I'm going to sketch out my standard normal curve here. Okay, just like sampling distributions, just like normal distribution problems, it's a good idea to just quickly sketch this for yourself. All right. Okay, just for you so that you know which direction you're looking when you do this on the Z table or you use your calculator. But notice that you're shading here to the left, right? And that correlates directly with your alternative hypothesis, right? Okay, so what we are actually calculating here is the probability. Oops, hold on. Let me switch this back to this font here, or this color. So we are finding the probability that p hat is less than 0.64. Okay, which is equal to the probability that Z, your test statistic, is less than negative 2.827. Okay, and then I plugged that into my calculator. I used norm CDF, okay, and I got 0.0023. Okay, you could use the Z table and you would get something very similar to this, if not exactly this value. Okay, and just as a quick note for you, you do not have to write both of these probability statements. You can just pick one of them. Okay, but it's important that you use at least one of them so that this number right here has a label of some kind, right? So that you're not just reporting a blank number with no meaning, right? Remember, statistics is all about connecting the numbers to the actual meaning and the context, okay? So make sure that you use at least one of these probability notations when you're writing this out, okay? Once you get to this point, you have done all the actual math here, okay? So the last two steps here, M and S, are all about your conclusion, right? And making a decision, right? So M stands for literally that, make a decision. So my p-value was 0.0023, which is less than alpha, which remember was 0.05. So that means I'm going to reject the null. Okay, so that's my decision. And that's my final decision. Okay. So then the last thing is to state your conclusion in context. So this is where you use your word formula, right? So you would say, because the p-value is less than alpha, we reject the null. Okay. We do have enough evidence to support the alternative hypothesis, and then you need to state what that is, which states that the true proportion of free throw shots made is less than 0.8. Okay, so that is an entire hypothesis test worked out. Okay, even though it is broken up into lots of steps, right? I'm hoping that having it broken up like this makes it a little easier for you to tackle each part, right? Each part is small, and you have just really one thing that you have to do at each step, right? Just state the hypotheses, right? Just check the assumptions, right? Just calculate the test statistic, right? So I'll let you all know, if you're doing a hypothesis test, these show up more often than not on the free response part of the AP test. I guarantee you, you will have at least one hypothesis test, like one full hypothesis test, or one full confidence interval, and that will be an entire free response problem. Okay, so you have to be able to do these hypothesis tests in about 12 minutes, right? 12 minutes or less, okay, in order to stay on pace to be able to answer all of the free response questions, okay? So when the AP readers grade these, you get points for all of these steps, okay? So they typically will give you these free response questions are scored out of 4, right? So usually they'll split grading these hypothesis test questions into 4 parts, right? Where you will get points for your prime parameter and hypothesis, and like naming your test, like selecting the proper test. You will get points for your assumptions. You will get points for obtaining the correct probability, so the math part, and you will get points for your conclusion, right? So all of these steps are necessary, right, in order to get full points, right? And the reason I split them up into these small parts is just in case you forget like what M stands for, or you forget what N stands for, right? That you can cover those things possibly in other sections, right? And you're going to get more points on your free response question that way. All right. Okay. So there's one other one-sided test here that I want you to try on your own. Okay. But I'm going to help you out and kind of get you started. Okay. So on shows like American Idol and The Voice, right? I don't know about you all if you wondered this when you were a kid, but I wondered this because this is how my math brain works. But I kind of always wondered if like how they determined the order that people went in, right? Because it's TV. So you have to put like the good performances, like the really, really good ones, the ones you think are going to be really awesome, like at the beginning or at the end. They're usually not in the middle, right? So we're thinking about here, is there an advantage to performing last? Because the general like psyche of people that are watching these shows is that, well, if we're getting close to the end of the episode, then that means this performance must be is going to be really good, even if it's not, right? So it's almost like a placebo effect, right? So we're trying to figure out, is there an advantage to performing last? Okay, so we have a random sample of 600 college students. They showed students an audition video of 12 different singers. Videos were shown in a random order. So we would expect 1 out of 12 of the students to prefer the last singer that they view, right? If we're assuming that the order of the singers doesn't actually matter, right? If you're assuming that the order doesn't matter, then that means the likelihood that a college student would choose the last singer's performance is the same as the likelihood of any other, right? Okay, so in this study, we had 59 out of the 600 that preferred the last singer. So the question is, do these data provide convincing evidence at the 5% significance level that there is an advantage to going last? On the AP test, this question would be, do these data provide convincing evidence that there is an advantage to going last? They wouldn't include the significance level because, one, they wouldn't want to give away that this was a hypothesis test problem, and two, they would want you to choose the significance level. Okay, this is a very common type of question where they're just asking you, is the data convincing? And you have to show whether the data is convincing or not. Okay, and the way that you show that data is convincing or not is using a hypothesis test. Okay, so you have in here a couple of important pieces of information. Okay, we have what we would expect to happen. We have what actually happened. So this is like P versus P hat, okay? And we have a sample size here, okay? So that's all the information you need. Oh, and we also know that this was a random sample. Okay, that's gonna be important, all right? So what I want you all to do is pause the video and on your own, try to work through these 8 steps. So work through the acronym and see if you get the same thing that I do. So go ahead and pause the video, try this one out, and then check back with me to see how you did. All right, folks, go ahead and check your answer against mine. So my parameter is the true proportion of college students who prefer the last singer. My hypotheses, my null hypothesis is that that proportion is 1 out of 12, which is 0.083. So this right here, this number is 1 out of 12. Okay. Now, if we are trying to prove that there actually is an advantage to going last, we would say that we think that that proportion, which is the proportion of people who prefer the last singer, is actually greater than 1 out of 12, so greater than 0.083. So that's my alternative hypothesis. Okay. Next, I have to check my conditions, my assumptions, okay? So random sample, that one's easy. It's stated in the problem, okay? 10% condition, I did 10 times the sample size and said that's 6,000. That's definitely less than the total number of possible college students they could have pulled, okay? And my large enough sample, right, that's my success fail, my large counts. So n times p is 50, n times 1 minus p is 550. Both of those are greater than 10. When you have a really large sample size, right, like 600, you often will get numbers like this that are pretty large. That's okay. You're supposed to, okay? Then next, I had to name my test. So this is a 1 proportion Z test because I'm dealing with proportions. There's only one sample. This is a test, and I'm using Z, not T. Remember, Z goes with proportions, T goes with means. Okay, and then they did give me an alpha value in this one. They told me to use the 5% significance level, so that's my alpha value, 0.05. All right, so that's the setup. Now we've gotten to the math part. So for my test statistic, I need P hat, which is the sample value. Right, so my sample proportion was 59 out of 600, which they gave me in the problem, and that's 0.098. My population claim, right, is 0.083. My sample size is 600. Then I calculated my standard deviation, 0.083 times 1 minus 0.083 divided by 600, all under the square root, and I got 0.0113. Then I'm plugging all of that into my test statistic formula. So I did my data point, which is the sample proportion, 0.098, minus my population value or my claim, 0.083, divided by the standard deviation, and I got 1.33, okay? So once we get to O, that's obtaining your p-value. So that's where you break out your z-table or your calculator to use normal CDF, okay? I wrote the probability notation 3 different ways, okay? So this is the first way, this is the second way, and this is the third way that I wrote it, okay? You do not have to write all of these. Just pick one, okay? the first way that I wrote it is in terms of the actual sample statistic. Okay, the second way that I wrote it is in terms of your test statistic, the Z value. And then the third way that I wrote it would be if you used a Z table, right? Because if you recall, the Z table is only going to give you probabilities to the left of a particular value. And here we're trying to find the greater than probability. So if you were using a Z table, you'd have to do 1 minus the probability that's associated with the number 1.33, like with that Z score. Okay, but either way you write it, the final probability you get is around 9%. So depending on if you use the Z table versus the calculator, you may get slightly different answers here. That's okay, right? There's definitely a margin of error, right, when the graders like actually grade this thing. And it won't be so large, like the differences between maybe what you did and what the actual answer is won't be so large that it'll affect your decision most of the time, right? Usually the changes are like down here in the 4th decimal place, okay? All right, now that we've done the math part, we need to make our decision, right? Remember, I set my alpha value at 0.05. So this p-value is above my standards, right? It has exceeded my cutoff value, right? So that means I'm going to fail to reject the null. Remember, when you say fail to reject the null, that does not mean you are accepting the null. It just means that we don't have enough evidence yet to reject the null. Okay, so that's essentially what you're saying in the last step, which is state your conclusion in context. So you would say, because the p-value is greater than alpha, we fail to reject the null. We don't have enough evidence to support HA, which states that the true proportion of college students who prefer the last singer is greater than 0.083. Okay, so we don't know for sure if it's actually equal to 0.083. We just know that we don't have enough or sufficient evidence with this particular sample, with this particular experiment, to disprove it, right? All right, you guys, so that is it for this video. And in the next one, I'm going to do a couple examples for you with two-sided hypothesis tests, which is very similar to this. The process is almost exactly the same. There's just a couple little tweaks, a couple little things that are different, all right? So I will see you in the next video. Bye, everybody.